Hi, so it's time to start now. So first, let me explain some important notices from AIP about this seminar. Re uh, Reproduction is prohibited, and reproducing all or any part of the contents is prohibited without the author's permission. And number three, this seminar will be recorded and the video will be available on the RIKEN AIP website later. And if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. Yes, so you can make questions anytime during the seminar, and just write down the question comments in the Q&A box. So someone may answer immediately or later. You can put questions, comments in the box, yes. And next, if you Q&A session, if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put a comment or question in the box. Hi. And also here the list of forthcoming seminars. So the URL is here, and so next seminar will be July 14th, and then subject is no, not subject, but it talks by medical risk avoidance based on IPSL team, and there are some other talks, so on. So please come again. All right. So I'm Hidetoshi Shimodaira, team leader of mathematical statistical team, RIKEN AIP. So first, let me give introduction to our team. So mathematical statistics team is a part of Kyoto University cluster with a Kyodai cluster, RIKEN AIP. There are several other teams in Kyodai, Kyoto University, and then we say Kyodai cluster. This is a building of a unit. And also we are making artificial intelligence research unit, AI unit in Kyoto University. So they are kind of equivalent. We have two different names. And this is a current member of our team. So here me, and then here Tom Pham, postdoc fellow, and other research assistants. They are actually students, PhD students and master students at Kyoto University. And these visiting researchers, they are actually faculties at the institutions. So today, this guy and then this guy and this guy will give talk following me. And so they are, actually not here, at the university, but this guy is actually associate professor at Kyoto University. So, kind like this. So here is the agenda of today's seminar. First, I give introduction and also some topic on natural language processing. And after that, three speakers follow. First, Akifumi Okuno. He's working at the Institute of Statistical Mathematics, and talk is on improved approximation capacity of graph embedding with sham neural network. And the next speaker is Yoshikazu Terada, working at Osaka University. The title is Selective Inference via Large-Scale Bootstrap and its application. And the last speaker is Son Pham, who is, Riken AIP, and he is actually in the building I saw the photo, so in Kyodai. And the subject is some recent progress in modeling preferential attachment of growing complex networks. So what we are working on is statistics and machine learning. So everybody do machine learning, but the flavor, is our flavor is some focus on statistics. And this is a website of a lab at the Kyoto University. In Japanese, 統計学 and 機械学習. And there are many related topics. So there are many figures here. And so also, I'm saying that our focus is on a data-driven methodology with statistical inference for artificial intelligence. And it's a kind of mixture of statistics and machine learning. And then I want to just try to mention that notion as a statistical intelligence. 統計知能. I just made this word quite recently, a few days ago. So this is the first time for me to show this word. People in the statistics and machine learning community, people say statistics and machine learning are kind of different, but for me, they are not much different. So just I don't want to really separate these things and just try to make some combined idea and then just try to give a level as a statistical intelligence. So there are several topics we are working on, but some of them are current research topics as follows. I just show 5 topics, and today's talk, 3 speakers from me are giving talks on this topic. The first topic is representation learning via graph embedding for multimodal relational data. So this is a kind of dimension reduction. So given a high dimensional data from several model, something like picture, figure, text, and also relational structure represented by graph among these nodes. So given such a data structure, we try to give some transformation from those input future vector to some embedding vector. So all those input vectors from several modality may be presented in a shared space. Okay, so this is not a really new idea, but includes many interesting topics. So this is what we are really working on. And so and then natural language processing, we are really interested in that topic, is part of that project in a lab. Okay, so later I'll give some introduction to this and also to this. And the next topic is valid inference by a large-scale bootstrap resampling for many hypotheses with selection bias. So this is a kind of method to give some confidence value to some data analysis. So it's a kind of hypothesis testing. So several ideas have been, proposed for this issue, and then multiple testing or false discovery rate or recently selective inference. But our focus or our own methodology is based on multi-scale bootstrap, which is a kind of strange idea in which we change the sample size in the bootstrap resampling, so to reproduce the simulated data from observed data, and then we extrapolate the sample size to -n given n observations. It's a very strange idea, but this method has been used quite a lot in life science, and then some of my papers are cited 10,000 times, and so this really works. Okay. And the third one is the statistical estimation of growing mechanisms from complex networks. So this is a kind of applied statistics, trying to understand the mechanism behind the growing networks like web, World Wide Web or SNS, something like that. So this is a very interesting topic. And the fourth one, so this is one of the machine learning topic, which is k-nearest neighbor. K-nearest neighbor is a very classical method, before any neural networks, so given several data sets, so you try to find the k-nearest data points from a given query point, and then try to compute the average of some output among those k neighbors. So, but there are sometimes this method works very well more than the deep neural network, and we give some nice idea on it. So let me explain later a little bit on it. And then the last one is merchant bandit and Bayesian optimization. So this topic is worked on by a new member, Junior Honda. So today he doesn't give a talk, but he joined quite recently in our lab. He's actually an associate professor at Kyoto University, as I mentioned. Okay. So before talking these three topics, let me explain a little bit on the fourth topics. This is because very interesting. Okay, I'm spending too much time as usual, so I have to keep my time. So this is kind of reconciling bias variance trade-off in k-nearest neighbor. What does it mean? First, let me explain what k-nearest neighbor method. So given query image, for example, try to find the k neighbor pictures. So now k equal 4. So you find the 4 pictures, which is closest, to given query, and then look at those levels, and then count how many times these levels are seen in these 4 neighbor pictures. So the cat tag shown 3 times among 4 pictures. So this is 3/4, 75%, we say, something like that. So this is k-nearest neighbor algorithm. But of course, this result depends on the choice of this k. So there's a dilemma, because if we make k very small, then the method becomes less biased. But obviously, variance is very large because we look at a very small number of pictures. So now we increase k like 1,000, then the result will be stable. But you look at a very, pictures very far from the query, then the result will be biased. So people try to find the optimal k, reconciling these two trade-offs. But our idea is not doing so instead. So this axis is distance from a query or equivalently kind of k, and then try to compute, k nearest neighbors at several k values like this, and then try to extrapolate these results to k equals 0. So we got some imaginary, which is non-existent, 0 nearest neighbor estimate. So this is unbiased, but at the same time, we using many samples, so variance is small. And then we can show that this is optimal, kind of. So this is interesting subject, but we didn't discuss this topic further, but just I want to say this. Okay. Next. Okay, so this is the first topic, actually by Okuno. So let me explain the background of this topic. And given feature vectors, so like this is a 2-dimensional feature vector, and then these faces are kind of some input vector, only 2-dimensional in this case. But so these are attributes, okay, 2-dimensional. And also we have some link weights, something like this guy and then this guy are friends, for example. Something, these, so links are representing those some relations among these nodes. So using these two inputs, we compute some linear transformation or nonlinear transformation by neural network, converting from xi's to yi's. And then now yi's are new feature vectors, we say embedding. And so these new feature vectors are trying to represent these link weights, Okay, so these relations as well, not only xi's, so that if these link weights are large, for example, this guy and this guy are somehow links, we have a link, then these two guys here also cross each other on the new features, something like that. And then these new embedding vector have something similarity measured by the inner product, and then this Sij may be related to this way to the link observed link weights. This is nothing but this idea includes many methods, many conventional statistical multivariate analysis like canonical correlation analysis, and also many others. And recently also this is generalized. We consider the generalization to hyperlink instead of just a link. So, as a theory, this includes many interesting methods. So we work on this idea. And this example, so in this example, we have MNIST images, and then also these levels. And then so this is 3 views, 3 domains, and then try to compute a transformation from these views to this 2-dimensional image, so that these levels as well as this input to image are represented in this new embedding. Okay, like this. Okay, so and we can apply these ideas to many examples. Even so, these are, we just consider the linear, but recently also consider non-linear and several interesting idea applications. And okay, I have to go fast. So this is a theoretical model. So given these input vectors, we transform these input vectors by neural networks to compute the embedding. Okay, so this can be linear or nonlinear by neural network. And then there are links, as I said, these links are Wij. So new embedding representing both those input vectors as well as these links. Okay. This is not new, actually, but as a special case, this is called sham neural network, proposed a long time ago. So given two handwritten, handwritten signature, transforming these to some vectors, y's by neural network, and then compute the similarity by inner product. So this is a very old paper. So our proposal is nothing much different from this. So here I said inner product. Of course, similarity can be any function, not necessarily in the product, but just I prefer to use inner product as a last level, because the these linguistic regularities should be based on this distribution law of inner product. The king minus man plus woman equals queen. This is well-known linguistic regularities or in natural language processing. And then the key idea is this distributive law. So inner product is a key here. So I stick to inner product here. But inner product is very restrictive, which only are able to represent positive definite similarity, so-called positive similarity. It is very wide, like which includes cosine similarity or Gaussian kernel, or actually kernel method, kernel. In kernel method, actually all they are positive similarity, positive definite similarity. So they are wide enough, but they actually not including these similarity measures like distance, usual distance, or Poincare distance, which is very popular recently. These are not really represented by inner product, but just modify a little bit. This is the original inner product, but modify a little bit like this way, like adding this bias time or giving some weight to the inner product. Then actually all these similarity measures can be represented by only these modified inner product. So this is very interesting topic. So Okuno will give more on this subject. Okay. And then this is kind of NLP. So this is a kind of next step of the representation learning research. So now we are interested in constructing a framework for reasoning with operations in a vector representation. This is a two-dimensional visualization of the world vector computed by kind of word to vec or globe. They are distributive representation of words in natural language processing. And look at king and queen and man and women. These are kind of this shape. That means there are kind of relations. This different vector is kind of vector from man and to woman. Man and woman. So we have some kind of operations. So if we do operation by vector addition and subtraction, we have here queen. Also here we have a sister by doing, and then this kind of operation really works. It is well known in natural language processing. So this is very interesting. But as I explained a little bit later, this is actually and operation. So it is one of operations which we could do. So there are other operations like or not. There are several more operations. So this is very interesting generalization we could work on for constructing a kind of nice artificial intelligence sort of by doing analogy computation. So this is a classical additive compositionality. So say queen may be represented like royal plus woman, and then king is royal plus man. So by removing this royal from this equation, we get queen equals king minus man plus woman. so this is additive compositionality. Queen should be addition of these two vectors. Okay, so this is well known. Okay, and then to get that representation, there are several methods to derive that formula, but we recently found a nice idea, which is, okay, this is the original model. So the word vectors, one of word vectors are based on this formula. I don't have time to explain details, but after some pre-processing, actually this is a very simple frequency weighted centering of these word vectors. Then we have this formula. And this is C is some word, and then W is another word surrounding some word, it's a context word. Okay, so in natural language processing, people say that properties of word is represented by the distribution of words in the neighbors of that particular word. Okay, so just look at the words around some word, then you can tell what this word is. Okay, so this distribution, this is a conditional distribution given word C. So probability of W, word of W given given word C is maybe represented like this way. And then once we assume this formula, then PMI, PMI here is represented this way. So based on this simple formula, we can show several interesting formula. For example, AND operation is like, so if W is AND of these S words, then we may have this formula. This is a kind of assumption. Then we can easily derive from this formula that like this. And then this should hold for any word C. That means this VW should be addition of these word vector. So this is a additive compositionality. So we can derive that like this way. And it's not new, but a kind of modification of the existing result. But we can also compute OR operation like this. So just changing the multiplication to addition, we can get a kind of this formula. So this is a kind of new formula for OR. Actually, this is not really new. Somebody else actually already proposed this formula based on other assumption, but we rediscovered this formula. So this is a difference, So people usually talk on this additive compositionality, but we can also work on this kind of OR operation. But and also we have further done that by introducing a conditional embedding. That is a new concept. Then we can also consider not operation. This is totally new idea. So I don't have much time, but what I can say is not operation, not vector is kind of negative vector of the original word given some small set. Not is very difficult concept, so not easily discussed. But so we have to specify some set of words before talking about a not. And then within that subset, not is complement of given some words. So we have to define not like this way. Anyway, so we can anyway compute and or and not, and also any logical operations on those words. Okay. This is the example. Let me skip this. And okay, so time is also running up. And so now I would like to explain a little bit on the third speaker, I mean, Yoshikazu Terada, who is his talk is on resampling, large-scale bootstrap for resampling for many hypothesis with selection bias. So I don't have much time, but let me explain some idea. So large-scale bootstrap is like, as I said a little bit, but so this is the original data, and then this is the resampled data. So we have assumed, say we have n data, for example, n equals 30, we have 30 items. And so in Bootstrap, we resample from these items with replacement, okay? And usually this n prime is same as n. So if original data is 30, then this replicate the data set also has sample size 30, of course. So this is what usually people do. But we can change this n prime to any value from n, So if this is 30, we can change this to say 60 or 15 or anything you like. And then compute Bootstrap confidence interval or Bootstrap confidence probability or anything by kind of simulation. And our idea is like extrapolating the result to n prime equals minus n. This is very unusual, as I said, but this works quite well. And if you look at the number of citations, these papers are cited 1,000 times, mostly from life science. And so people think the method works. And actually, the method is based on very, mathematical idea, kind of curvature of hypothesis surface in parameter space of probability distribution, something like that. So there's a kind of solid theory behind that, but people don't really look at that just to use it. But anyway, this is very interesting idea. So this method has been used quite a lot, but today's talk has focused more on selective inference. So Bootstrap resampling and the large-scale Bootstrap, as I said, is originally not for selective inference, but ordinary inference, usual p-value. But recently, selective inference is very important idea because, as you say, there are often discussed the selection bias is problem, or publication bias, or file drawer problem is issue. For example, if you have collecting some data set, and then and then some data is really good for you, but other data is not really good for you, the result is not favorable for you, then you may just throw away such a kind of data and only collecting the data set which you like, and then make some publication only from that kind of data set. So that's what people shouldn't do, but people do. So publication in well-known famous journals, Nature Scientists, they could be full of false discoveries. But we can adjust that kind of bias if we know the process of the selection. So of course, we don't know what the people do behind the door, but in some situations, like formal model selection, lasso, or any model selection AIC, you have a selected number of variables and then do testing or confidence intervals for selected features. So in that kind of selection, we know the selection process formally, and then we can adjust that effect of selection. So well, I skip these things, but now this kind of inference is called selective inference or post-selection inference. And so large-scale Bootstrap is also modified to this selective inference. So this is the subject of Professor Terada. Okay. And then the last one is the statistical estimation of growth mechanism from complex networks by Song Pham. So this is about growing networks like this. Okay, I have to go fast. So given time series of networks, for example, if you got a social network, friend network at some time, and then every month you get this network data, and then collecting them for 2 years. So you have your friends growing networks, right? You have that data. Then given that kind of data, you can estimate growing mechanism. What kind of node, what kind of people get more friends like that. So the main mechanism is preferential attachment. That means if you have more friends, then you get more friends. I mean, rich get richer effect. This is well known. So this is a very interesting topic. So Professor Pham, Dr. Pham will work on, he is working on that statistical estimation of that mechanism. And recent progress is, that he recently developed a method which estimate that mechanism without a time series of networks, but only one shot of network. So given just one network, probably the latest network, friend network you got. So only that data without a time series of networks, you can estimate a growing mechanism. So that is really interesting. But when he's developing the method, he found that something wrong. So here, this is a simulation. So in theory, this is a true mechanism, preferential attachment mechanism. And then baseline method estimate like this, something strange effect appears. But properly adjusting something, we get a nice result, this proposed method. The idea is actually selective inference. That means, if you look at the larger case, something K is a number of links for each node, you don't have a data points for all the K values. That means for this range, K equals 1, 2, 3, up to 10, the data set is dense. So you have many nodes with the number of links, that number. But if the K equals, say, 1,000, maybe we may have a nodes with K equals 1,000, but we may not have a nodes with K equals 1,005, something like that. So we don't have all the K values, okay? So we have a data set only for the observed K, obviously. That means we have a selection bias. So if we properly adjust that effect, we get a nice result. That's what Dr. Pham talks. Okay, so now I finish my talk. If you have any question, I may answer, but if you don't, you can do question later. And then going to the first speaker, Professor Okuno. Is okay? Nobody questions?
Yes.
Okay, so Okuno-san, please start your talk.
Okay, thank you very much, Professor Shimodera. Hi, and my name is Kimi Okuno. I'm assistant professor at the Institute of Statistical Mathematics. And I'm also a visiting scientist at the mathematical statistics team of RIKEN AIP. And today I'm going to talk about our study, improved approximation capability of the graph embedding with Siamese neural networks. And actually this work is a joint work with Professor Shimodaira of Kyoto University and Associate Professor Keisuke Yano of the Institute of Statistical Mathematics and Mr. Kim of NEVA, who was a master student of Shimodaira Laboratory. And actually this talk is based on these 4 papers published in AI Stats, Ichikai Neural Networks, and Archive. So if you are interested in this talk, please refer to these papers. Okay, anyway, let's get started. And okay, this slide shows a summary of this talk. And in this talk, we consider graph embedding, which is a node representation learning of a graph. Oops. A graph, and for a graph embedding, and actually graph embedding computes a feature vector of nodes, and the feature vectors which are computed by graph embedding can be used for statistical tasks such as clustering and visualization. So the graph embedding is a kind of preprocessing of the data analysis. In this talk, we propose some expressive similarities for the graph embedding methods. And here I note that the graph embedding used in this study is not a graph neural network. We employ a simple Siamese neural network, but not a graph neural network. Okay. Anyway, the detailed settings are explained later in this talk. So let's go ahead. Sorry. Okay, and for describing the details of this talk, at first, I explain the dataset structure. So please look at these 2 figures. I showed 2 different examples of the network with attributed nodes. These networks are called attributed networks. Please look at the left one, and the left one is called the co-authorship network. And in this co-authorship network, the node, this one, represents the researcher. And the node covariate x1 represents the number of papers written by this researcher. For example, this researcher 1 have published 2 papers in conference A and 3 papers in conference B and 0 paper in conference C. So then the covariate x1 of this researcher should be 230 or something like that. And similarly, this researcher 2 published 5 papers in conference A and C and 0 paper in conference B. So the covariate x2 for this researcher 2 should be 505 or something like that. And in addition to these node covariates xi, we observe the link weight yij, which represents the number of co-authored papers written by the pair of researchers in this example. For example, there is a link between two researchers, 1 and 2. So the researcher X1, X2 should have some co-author papers. Okay. And although we may employ some binary valued link weights Yij in this example for describing the existence of the co-author papers, but we can employ some integer link weights for representing the number of co-author papers written by these two people. So in general, we do not restrict the link weight Yij to be binary value. Link weight Yij can take real values in general. Okay, so this is the explanation of the co-authorship network. And the right one is called the friend network. And in this example, the node represents the people, and the node covariate xi represents the feature of people like age, gender, etc. And the link weight represents the friendship. There is a link between these two people, so these two people should be a friend. And maybe you can imagine some social networking services for this friend network. So these are the examples of the attributed networks. And using these kind of networks, we consider a link prediction problems, which predicts the link weight Yij, this one, from the pairs of the covariates xi and xj. Okay. And for predicting the link weight Yij from the pair of node covariates, we train a function g theta such that the inner product of this function outputs approximate the link weight Yij. If Yij is binary, we may apply some sigmoid function to this inner product. And typically, we utilize neural networks for this function g theta to attain the high expressive power. And so the link weight Yij is predicted from this prediction function. So this is a kind of link prediction. And okay, and the function g theta, this one is trained by minimizing this loss function L theta, which is a kind of distance between the observed link weight Yij and the predicted values. And if Yij is binary, then we may employ some logistic functions to train these neural networks. But the loss function depends on the range of the link weights Yij. So for example, if Yij takes all the non-negative values, we can use Kalbach-Leibler divergence. And if Yij takes real values, then we can employ a squared loss function or something like that. And actually, for loss function using general Bregman divergences, we proved the statistical consistency. So we can use any of Bregman divergence-based loss functions for learning the similarity function. But in this talk, for simplicity, we consider only a binary link weights and logistic loss functions. But the remaining results can be applied to more general class of link weights and loss functions. So as a summary, by minimizing this loss function, we can train the function g theta, and then we can predict the link weight Yij by applying this similarity function defined for node covariates. Okay, and then once the neural network g theta is trained by minimizing this function, as I explained in the previous slide, the link weight Yij is predicted by the inner product between two neural network outputs. So then the neural network output, which is written by zi here, can be used as a new feature vector of the node I, because the feature vector zi is transformed from xi, and the neural network g theta is trained to approximate the link weight Yij. So zi is expected to contain the information of both link weights Yij and the data vector xi and the covariate xi. So the feature vector zi can be used for downstreaming tasks such as clustering or visualization. And actually, if the output dimension of the function g theta k is less than the output dimension is less than the input dimension, then the graph embedding can be regarded as a kind of dimensionality reduction methods like principal component analysis. So graph embedding is a kind of preprocessing of the data analysis. So this is our explanation of the graph embedding and link prediction problems. Okay. And okay, for predicting the link weights, we used the inner product between the neural network outputs G theta xi and G theta xj here. So, and we especially call this similarity based on the inner product as the inner product similarity IPS model. And also many of existing studies employ this IPS model. Some recent studies employ other distances. For example, Poincare embedding, which was proposed by Nickel and Keeler, employs the Poincare distance instead of this inner product. And some other studies employ other distances, such as the square distance. So we can employ a variety of the distances for the prediction function. So simply, we can generalize the prediction function like this. So using the neural network G theta and the kernel V, the prediction function which applies the kernel V to the neural network output, this one is called the Simus neural network. And please look at this figure. Can you see this one? Please, this figure. And in this figure shows the Siamese neural network. And in this Siamese neural network, the neural network G theta is applied to each node covariate xi and xj. And then we obtain the feature vector zn and zj. And the similarity between these two feature vectors is measured by the kernel V. And actually, this Siamese neural network reduces to the conventional prediction function of inner product similarity models by assuming that the function V is inner product. And this similarity also reduces to the prediction function of Poincare embedding when we apply the Poincare distance, when we use the Poincare distance here. So we employ arbitrary kernel V for the function, for this prediction function. So in this study, we designed the kernel V for this one, for maximizing the expressive power of the prediction function defined by this. So this is the purpose of this study. Okay. And for maximizing the expressive power, we first consider the expressive power of the conventional inner product similarity models. Actually, in this model, we use the neural network G theta inside the inner product. And by virtue of the expressive power of the neural network G theta, it is expected that the IPS model has high expressive power. So natural question for this IPS model is, can this IPS model approximate any function H star which is defined for the covariate xi and xj? And the answer is actually no. Although this neural network G theta is sufficiently expressive, applying the inner product restricts the expressive power. And actually, the inner product similarity can approximate any positive definite similarities. Okay, here we define the positive definiteness of the function h. A similarity function h is said to be positive definite if and only if the quadratic form, this one, is non-negative for any pairs of the coefficient ci and covariate xi. For example, of course, the inner product is one of this PD similarity, and the Gaussian kernel is another example of this PD similarity. Then we can prove that any positive definite similarity H can be approximated by some inner product similarity using a sufficiently large neural network with sufficiently large output dimension K. And actually, the proof of this theorem is simply obtained by Massar's theorem and the universal approximation theorem of the neural network. And for understanding this theorem, we show a simple example in the next slide. Okay, this is a simple example of this theorem. And please look at the left figure. The left figure shows a Siamese neural network using a positive definite kernel, VPD. And this neural network, this Siamese neural network applies the kernel VPD to the neural network outputs G star Xi and G star Xj here. And our theorem states that as long as the positive definite kernel VPD is used for this Siamese neural network, then the overall neural network, this one, can be approximated by the inner product similarity model equipped with sufficiently large neural network G star, G theta with sufficiently large output dimension K. So as long as the positive definite kernel VPD is employed for this Siamese neural network, the expressive power of the Siamese neural network is eventually the same as the IPS model. So there is no need to employ other PD kernels for graph embedding as long as we can utilize the IPS model. So this is what our theorem says. But actually, the IPS model cannot approximate any non-PD similarities. Namely, the IPS model is limited to approximate only the PD similarities. So, and we can theoretically prove the limited approximation capability of IPS model. And actually, we can examine the limited expressive power of IPS by numerical experiments like this. And in this experiment, we try to approximate a non-PD similarity by using the IP inner product similarity model. And as you can see, the IPS model fails to approximate the ground truth function, which is non-PD in this experiment. So for approximating even the non-PD similarities, we propose a shifted IPS model. And the shifted IPS model is defined by incorporating a simple neural network U to the existing IPS model. Then we can prove that the proposed Ips model, this one, can approximate any conditionally PD similarities. Actually, CPD similarity, conditionally PD similarities generalizes the PD similarities. So the proposed Ips model has higher approximation capability than the conventional IPS model. And actually, Ips model incorporates only one simple neural network to the IPS model. So the implementation of the Ips model is very easy. So it's very practical. And I show the definition of the conditionally positive definiteness here. Similarity function H is called CPD if and only if this quadratic form is non-negative for any pairs of coefficient Ci and covariant Xi, where the sum of this coefficient is restricted to be 0. Okay, and actually, if the function H is CPD, then the function also satisfies the definition of positive definiteness. So the CPD similarities include all the PD similarities and some non-PD similarities like negative square distance and negative Poincare distance, etc. And here I show some experiments on approximating CPD similarity. So as I showed in the previous slide, the existing model cannot approximate the ground truth function, this one, but the proposed Ips model can approximate the ground truth, as the ground truth function here is CPD. So this numerical experiment visualizes the high expressive power of the proposed Ips model. Okay, and this slide also shows the prediction mean squared error of the IPS and Ips models. Okay, and we tried to approximate some CPD similarities by the IPS and Ips models. And as you can see, the error of Ips model, which is shown as the blue line, is much less than the error of the IPS model shown as the black line. So we can observe the high expressive power of the proposed Ips models in these numerical experiments. Okay, and we skipped this slide, but we can evaluate the approximation error rate for IPS and Ips models by simply applying the error rates of the neural networks to our settings. Okay, so we can obtain the approximation error rates. Okay, and as I explained, the Ips model has higher approximation capability than the IPS models. But actually, Ips model can approximate only the non-CPD similarities. So I mean, Ips model is limited to approximate CPD similarities. So we can prove that the Ips cannot approximate any non-CPD similarities. So more expressive similarity is preferred for universal approximation of the similarity function. So for attaining the higher expressive power, we also propose weighted IPS model, Ips model. This Ips model is simply defined by the weighted inner product between two neural network outputs. And in this Ips model, the weights W in this inner product is also trained with the neural network by using some optimization algorithms like stochastic gradient descent or something like that. So then we can prove that. Under some assumptions, the Ips model can approximate any continuous and symmetric similarity H. So the Ips model attains the universal approximation of any continuous and symmetric similarity. So this is a proposal. And okay, this slide shows the summary so far. In this talk, we first proved that the IPS model can approximate positive definite similarities, but actually, IPS model is limited to approximate PD similarities. And the proposed Ips model approximates CPD similarities. And CPD similarity includes all the positive definite similarities. So Ips model is more expressive than the IPS models. And furthermore, we proposed a Ips model, and Ips can approximate arbitrary continuous and symmetric similarities. Actually, we proposed another similarity called IPDS, and its expressive power is the same as Ips model. But we skip IPDS in this talk because we have no time today. Okay. So we conducted some additional numerical experiments here. Please look at this table, and this table shows the link prediction accuracy with some proposed similarity functions. We tried to reconstruct the graph and predict new links in hypertext network, coarser network, and taxonomy networks. And the prediction accuracies are evaluated by the ROC AUC scores, and the higher score is better here. And as you can see, the proposed Ips and Ips models show better prediction accuracy compared with the conventional IPS and Poincare models among all the experiments. And also please see this table below. And this table shows the classification accuracy of the node feature vectors, which are computed by the graph embedding. In hypertext network, there are two different types of labels of nodes. And for both types of labels, the proposed Ips model and Ips model outperform the existing inner product similarity model, Poincare embedding, and hyperbolic embedding, which is another implementation of the Poincare embedding. So we can see that for all the experiments, the proposed Ips and Ips model outperform the conventional IPS and Poincare models. Okay. Okay, so far I explained the expressive power of the graph embedding. And in the remaining of this talk, maybe I have 7 or 8 minutes, I will explain some more recent results on the non-parametric link prediction and embedding towards reliability evaluation. And the results are also uploaded to arXiv. So if you are interested in this topic, please read our paper. As I explained, we tried to solve link prediction and graph embedding. And for link prediction problems, we can define a kernel smoother for the link prediction as written in this slide. We employ a kernel KH here, which is regulated by the bandwidth parameter H. And the lambda n here is a regularization parameter. And actually, similarly to the conventional regression, this kernel smoother for link prediction is statistically consistent, meaning that the estimator converges to the conditional expectation of the link weight as the sample size n goes to infinity. Then the kernel smoother, this one, approximates. The kernel smoother approximates the link weight y. And actually, it reduces to the inner product between two embeddings gx and gx dash by assuming that the regularization parameter is 0. So we can obtain the graph embedding by considering even the non-parametric link prediction. And actually, in this study, we apply non-parametric theories to this kernel smoother for link prediction to evaluate its reliability. And actually, the observations in these non-parametric theories are expected to be applied to some parametric models like neural networks in the future. Okay, and for evaluating the reliability in asymptotic theories, I explained the designs of covariate xi called fixed design and random design. And as I explained, the covariate xi denotes the feature of nodes. And in the fixed design, the covariate x is assumed to be a fixed constant, and only the link weight y is random. For example, the regular intervals like 1 over n, 2 over n, blah, blah, blah is a fixed design. And in the random design, both of the covariate x and the link weight y are random variables. Actually, the uniform distribution is an example of the random design covariate. And actually, we cannot identify the underlying covariate design in some situations, but we need to assume either of fixed or random design for utilizing some asymptotic theories. From my personal experience, the people studying statistics tend to employ fixed design, and the people studying learning theory tend to employ random design. Well, this is my opinion. And fortunately, actually, the covariate design does not affect the asymptotic behavior of the conventional non-parametric regression. Actually, some papers proved that the fixed and random designs are asymptotically equivalent for the conventional regression framework. We can observe the asymptotic equivalence in the numerical experiments. So please look at the histogram. And in this experiment, we computed the histograms of the predicted values of the conventional regression. And as you can see, the histograms for the random and fixed designs are almost the same. So we can ignore the covariate design difference in practice if we consider conventional regression. But actually, in the case of link prediction, the histograms for these two designs are totally different. And as you can see, the histograms for the fixed design covariates are concentrated to the center. So these histograms indicate that the asymptotic variance of the link prediction depends on the covariate design. So we cannot ignore the covariate design difference in link prediction, unlike the conventional non-parametric regression framework. So this is a main observation of this study, and we think that this phenomenon is not well known in the community of both non-parametric theories and link prediction. And actually, many of existing studies on the reliability evaluation of link prediction do not care this design dependence. So some papers assume the fixed design, and some papers assume the random design without any consideration. And actually, we could ignore this design difference when considering the conventional regression, but we cannot ignore this difference in the link prediction problem. So this study just raises a problem. Okay. This slide shows the intuition behind the covariate design dependence. In the fixed design, the asymptotic behavior for link prediction is almost similar to the conventional regression. But in the random design, the link prediction and actually non-degenerative statistic have very similar asymptotic behavior in random design. So the asymptotic variance are different for these two designs. Okay, I have no time, so I skipped some slides. We conducted some numerical experiments with changing boundaries. And as you can see, for all the boundaries, the histograms for fixed and random designs are different. So regardless of the boundaries, the asymptotic behavior depends on the covariate design in this non-parametric link prediction. Okay, and actually fixing this problem is an ongoing work. I have no great idea yet for fixing this problem, but assuming random design is a conservative choice, so I recommend to use random design if we need to evaluate the reliability score for the link prediction problems or graph embedding. So we just raised the problem in this archive paper, but I think that we need to care more on the covariate design when considering the link prediction problems or graph embeddings. Okay, so this slide shows the conclusion. In this talk, we considered the expressive power of the graph embedding by using the link prediction function. And we proposed some expressive similarities. And we considered the link prediction reliability by applying some non-parametric theories. And thank you very much for listening. And if you have any question, please feel free to contact us at this email, something like that. So thank you very much.
So I'm Yoshikazu Terada from Osaka University, and I also belong Riken AIP as a visiting researcher. Today, I would like to talk about the general approach to selective inference for hypothesis testing of the null hypothesis represented as an arbitrarily shaped region. And this work is a joint work with Professor Shimodaira. Okay, here is the contents of our talk. At first, I explained the motivation of our research, and our motivation is a bit different from the common selective inference problem. And next, we introduce the general setting and describe our new method for general framework, general selective inference problem. And finally, we show some numerical results, including PV class example, which indicate our method reasonably works well. Okay. So now we briefly introduce selective inference. So recently we get a huge number of data set, and also structure is really complex. So exploratory data analysis is usually used to discover useful information from such kind of complex and large data set, and to also use to formulate hypotheses for further data analysis. And for the such hypotheses obtained by the exploratory data analysis, classical statistical inference is commonly performed. But in the phase of classical inference, effects of hypothesis selection based on the data are often ignored. However, this kind of naive approach provides an optimistic result due to the selection bias. So recently, inference handling the effect of hypothesis selection appropriately is called selective inference or post-selection inference, and it had been attracted much attention, especially on the inferences after model selection. Okay. So now we explain the motivation of our research. So one of the main purposes of this research is assigning the confidence level of each obtained cluster or clade in the estimated phylogenetic tree from DNA sequencing data, or in the hierarchical clustering. And evolutionary trees are often estimated from DNA sequence data. And this DNA sequence data shows a part of dataset used to construct phylogenetic trees for yeast. And the data are aligned sequences of DNA gene from 8 different species of yeast. And this figure shows a phylogenetic tree constructed from this dataset. And the tree building algorithm proceeds in two main steps. At the first step, an 8 times 8 distance matrix D hat is constructed for 8 species, measuring the differences between these row vectors in the DNA sequence data. And next, D hat distance matrix D hat is converted into a tree by a connection algorithm such as the single linkage method. And here we have an important question. So how much confidence should we have in the estimated cluster in the tree? And Professor Felsenstein suggests the use of Bootstrap to answer this question. And Felsenstein's method is a straightforward application of the Bootstrap, and which is widely used in the biology. Okay, now we briefly explain the Felsenstein's method. And Felsenstein's method proceeds these steps. So a Bootstrap data matrix X asterisk is formed by randomly selecting n columns from the original data matrix with replacement. And then the original tree building algorithm is applied to each Bootstrap data matrix and giving a Bootstrap tree. And this whole process is independently repeated some large number b times, say, for example, b equals 10,000, like that. And we calculate the proportions of Bootstrap trees agreeing with the original tree. So this is the algorithm of Felsenstein's method. Okay, then we can get this kind of confidence level for each cluster. Okay, this is shows the estimated phylogenetic tree based on the malaria data matrix with confidence values of Felsenstein's Bootstrap method. If we focus on this cluster, we can see the 96.5%. And this means that, for example, if we repeat 200 times Felsenstein's procedure, so then we have this credit is appeared 193 times in the 200 Bootstrap tree. So then we can get this confidence level. Okay, and Felsenstein's method is nearly a standard application of non-parametric Bootstrap. And so it seems this Bootstrap probability can be interpreted as standard statistical inference, such as p-values or hypothesis testing. Okay, in fact, Professor Efron argued the Bootstrap probability can be interpreted as a frequency confidence measure in the Felsenstein method. And we need the basic assumption to do so. The columns of data matrix X are independent of each other and are drawn from the same probability distribution. And of course, if this assumption is a bad one, then Felsenstein's method goes wrong, but that is not the point of concern here. And of course, we can relax this assumption for a general process, stochastic process satisfying a mixing condition. And under this assumption, the Bootstrap confidence values, it depends on the simple multinomial probability model in this example. And let's let X be the Q times N original data matrix, and there are K possible column vectors for the original vector, because now we consider four alphabet character to represent the data set. And number of vectors of length Q based on a four-letter alphabet, and not containing the four monotonic ones. So there are this number of possible column vectors. Okay, and these vectors are denoted by small x k. Okay, and suppose each observed column of the original data matrix X is an independent selection from these vectors, equaling xk with the probability pi k. Okay, so this is a multinomial model for generating a data matrix X. And the data matrix X can be characterized by this kind of proportion. And the distance matrix D hat is a function of this observed proportion in this setting. Okay. So under this model, we can define the true phylogenetic tree as a large sample limit. And the vector of true probability pi gives a true distance matrix D. For example, in this paper, they consider the very simple distance function. And these characters are interpreted numerically as these integer, respectively. And the distance matrix D hat is just a matrix of Euclidean distances between rows of data matrix. So in this case, the true distance matrix D will be the matrix with these elements. Okay, and then the true tree is defined by applying the specific tree building algorithm to this true distance matrix. And based on this model, we can interpret Felsenstein's Bootstrap confidence level of certain cluster as approximation of 1 minus p-values for the null hypothesis. Such cluster is not true. That means such cluster is not appeared in the true tree defined previously. Okay. And of course, this is not related to our current research, but this Bootstrap confidence level can also interpret it as a posterior probability of such grade with an informative prior. Okay. So this is an image of the hypothesis. Okay, and this idea can be extended for the problem to assign the confidence of each obtained cluster in hierarchical clustering. And this implemented in R as a package PV_clust. And for each estimated cluster, PV_clust provides the frequencies confidence measures to assess the confidence of clusters. And the PV_clust is very commonly used in the biology field. Okay. But in PV_clust, null hypothesis is an obtained cluster is not true. So the hypothesis is tested only for the clusters appeared in the obtained tree. So obviously, we need to perform the selective inference even for the PV_clust. So this is a motivation of our research. But unfortunately, in the existing research, we mainly consider the case in which it is easy to access the parameter space, or we know the explicit form of the region on the data space, which presents a selective region. But on the other hand, in some real application problems, such as PV cluster, we cannot directly apply this method. So in this talk, we provide a general framework to the selective inference for hypothesis testing of the null hypothesis represented as an arbitrarily shaped region in the parameter space. Okay. And we employ the general setting of the problem of region by following the simple setting of Efron and Tsushirani in 1998. And let Y be a random vector of dimension m+1 for some integer m, and the small y be its observed value in the Euclidean space. And our argument is based on the multivariate normal model with unknown mean, nu, and the covariance identity. And this normal model is a simplification of reality. And let X be a sample of size n. We assume there exists an appropriate transform, which may depending on n, from X to Y, so that Y is appropriately normalized. So we consider this simple model. So using this framework, bootstrap probability can be interpreted as the frequencist p-values. So ideally, the p-values should satisfy this equality for all mu on the boundary surface of the null hypothesis region. So this is called unbiasedness in statistical community. However, the accuracy of bootstrap probability is not high. So if the unknown parameter mu is located at the non-flat boundary surface on the hypothesis region, so then the rejection probability of testing based on the bootstrap probability is far from the prefix significant level, for example, 5%. So for example, if mu is located, unknown mean vector mu is located on this boundary, so then the rejection probability is not equal to the 5%, very far from the 5%. This is another example. Yes. So as a frequencist confidence measure, bootstrap probability has a serious bias. And fortunately, if we obtained some geometric quantities of about the hypothesis region, we can compute more accurate p-values. For example, in this paper, they consider this kind of p-value, and this kind of p-value provides a more accurate result. Okay. But however, in general, it is difficult to describe the model space explicitly, and so we cannot get the geometric quantities of the hypothesis region directly. So we cannot widely apply this approach for real-world problem. So to overcome this difficult problem, Professor Shimodaira proposed multi-scale bootstrap method. And multi-scale bootstrap changes the sample size of bootstrap replicate, whereas in the classical bootstrap, we set just a sample size of bootstrap as one of original data. And in the multi-scale bootstrap, we change the sample size. So based on the scaling law of bootstrap probability with the sample size, we estimate the key geometric quantities of region to fix the bias. So now I briefly explain the idea of multi-scale bootstrap. So let Y asterisk be considered as a bootstrap distribution with scale sigma squared. And we will denote the bootstrap probability of hypothesis by alpha sigma squared. And AH is the hypothesis region. And this figure shows changes of bootstrap probabilities at the different scales. And each line shows a different setting related with the signed distance. So this is this signed distance from Y observed data to the boundary surface with the fixed mean curvature. And we can see the so scaling law of bootstrap probabilities are different each other related with the signed distance. So this is the value of signed distance. Okay. So when we have the bootstrap probabilities at several different scales, we can estimate the geometric quantities such as the signed distance from Y to boundary surface and the mean curvature. More formally, under the classical large sample setting, we can get this scaling law of the this normalized Z value. So in which the geometric quantities appear as a coefficient of the simple regression model. And here, bar phi means upper tail of the standard normal, upper tail probability of standard normal. Okay, so using this psi transform of bootstrap probability alpha, we have this figure. And broken lines are the result of simple regression. And we can see the signed distance and the mean curvature of the surface at the projected point are correctly estimated from only bootstrap probabilities at various scales. So because in this setting, we signed distance is, for example, in the blue line means represents a case, signed distance equal to 1.1, and we can correctly estimate that value only based from the bootstrap scaling law. Okay. And in this example, we considered three settings in which observations are corresponding to this point, respectively. So since the projected points of these points are the same, so the mean curvature at this point should be same. So the slope of these three settings are the same in this example. Okay, to consider the general selective inference using multi-scale bootstrap, we introduce a selection region or selective region in the model space. So if observation Y belongs to the selective region S, so then we perform, then H is selected for the hypothesis testing. So in the PV class, previously explained, we set the selective selection region S equal to the complement of hypothesis region. Okay, so our goal is to do the selective unbiased test, which controls the conditional rejection probability. That is, we want to compute the p-value of selective inference satisfying this equation. And this satisfying this equation approximately such p-value is referred as the approximately unbiased selective p-value. And as described later, the computational cost of our method is low, and this accuracy is relatively high compared with the naive Bootstrap method. Okay, so as a remark, we mentioned for the non-selective situation, approximate unbiased p-value means satisfies this equation. So now we consider the selective setting. So we need to be considered a selective rejection probability. Okay. So now we put the additional assumption for multi-scale bootstrap. Let X asterisk be the bootstrap sample with size n prime by applying the same transform as Fm used for X, transformation of X asterisk follows this normal distribution. So now here we assume this assumption, and that H hypothesis region is unchanged for Y asterisk. That is the important point. And the normalizing constant is square root n for many situations, and the scale sigma squared equal to n divided by n prime in general. Okay. And all we need for computing the selective p-values, bootstrap probabilities at several scales. This is an important point. So we can easily get this probability by performing non-parametric bootstrap in real application with different sample sizes of bootstrap replicates. So we do not have to know the number of dimension m, and also the explicit form of the transformation Fn. And also, we don't have to know the shapes of the selective and hypothesis regions. We just assume the existence of such transformation to the multivariate normal model. And this fact leads wide application and robustness to the deviation from the multivariate normal model. And I will skip the details due to the time limitation. We provide theoretical guarantees for our proposed method described later. And we consider the two different symptotic theories to deal with smooth boundary and non-smooth boundary settings, respectively. Okay. So in this talk, we propose this selective p-value. And this selective p-value has a second order accuracy in the classical large sample theory. And the numerator of the proposed p-value is just a non-selective approximate unbiased p-value. So this is just a non-selective p-value. And we adjust the effect of selection by this term. And based on the relationship between the bootstrap probabilities and the geometric quantities in the model space, the proposed method can be considered as a bias correction using these geometric quantities. Okay, this is the mean curvature, and this is signed distance. Okay, so the algorithm for computing the proposed p-value can be decomposed into two main parts. At the first step, we estimate just the key geometric quantities of selective and hypothesis regions, such as the signed distances and the mean curvature at the boundary surface of the hypothesis region. And then we just compute the approximately unbiased selective p-value using these estimated geometric quantities. That is our proposal. Okay. And the computational cost of our algorithm is the same as the usual classical bootstrap method. And proposed method has two nice properties. First is we use only binary responses, whether the bootstrap sample is in the hypothesis region and it's in the selective region. And the second is we just resample from only the original data instead of the null distribution. So we can widely apply our algorithm. So if you are interested in the theoretical result, please refer this archive paper. And now let us consider the hierarchical clustering of long dataset, which is available in PV class package for microarray expression profiles of 916 genes for 73 tissues. Okay, and the tree building process is quite similar to the paragenetic inference, and this figure shows the result of our proposed selective inference with non-selective p-value. So selective p-value, selective confidence level is represented by blue color, and the non-selective one is colored by red. Okay. And if we focus on this cluster, it is very natural to use a non-selective p-value because scientists may emphasize the 6 tissues are different from others before looking at the data. However, most of the other cluster, we should use the selective p-value because they discovered only after looking at the data. Okay, and if we focus on this part, we can see the difference between the selective inference and the non-selective one. And in these two cases, non-selective p-value provides an optimistic result, but we can correct the selection bias using our method, and we can provide a correct confidence measure for these two clusters. Okay, so now it's time. So recently, our package PP class was updated, and so you can compute the selective p-value using the current PV class package. So maybe I finish my talk at this time. Thank you for your attention.
Hi, thank you. Any question or comments? There's one question. In terms, okay, so there's a question. In terms of accuracy, how much improvement do you see? In terms of accuracy, how much improvement do you see? Terada-san, could you answer the question?
Okay, just a minute.
So
the classical naive bootstrap probability is just first order accuracy. That means the bias term is reduced as order square 1 divided by square n, root n. But our approach provides the second order accuracy. That means the bias term is reduced like order 1 divided by n. That is a big difference. But sorry, now I cannot show the actual example. But if you are interested in the actual difference, I will show later. That's okay.
thank you very much. So please start your talk.
Yeah, thank you. So today I will talk about some of our recent work on modeling referential attachment in growing networks. So before we start, please let me introduce myself. I got my degree at Osaka University in March 2017. And from April 2017, I have been a postdoc at RIKEN. So I'm interested in computational statistics and complex network modeling. So first, I will show you some examples of the types of real-world networks we are interested in. On the left, this is a network in the brain of a worm. Next is a portion of the World Wide Web. The third one is an electrical network. And finally, this is a collaboration network between actors. So our main motivation is to analyze how these networks grow in order to predict their large-scale structural properties, or to discover interesting connection patterns or interesting nodes, or to find methods to facilitate desirable properties or to impede undesirable properties. Now we move to the first topic of today's talk, which is a review of the problem of estimating network growth mechanism with time-resolved data. Before going to the problem formulation, I will first describe why we need growth mechanism in the first place. I'm going to do so by explaining a serious limitation in one of the network models without growth. One of the classical network models is the Erdos-Renyi models. In this model, the network size n is fixed in advance. Two nodes in the model are connected with probability p independently of other nodes. In this figure on the left, here is an example to show that the ER model cannot capture heavy tail degree distributions observed in real-world networks. The yellow dots are the degree distribution of a proportion of the Google plus followership network. I fitted the ER model to the Google plus data and then plotted the degree distribution of the fitted model in blue. As you can see, the estimated ER model cannot reproduce the observed degree distribution, especially the heavy tail. In order to capture heavy tail degree distribution, we will need growth and referential attachment. So here is an example of a growing network. The network starts from some initial state at time step 0, and then with each time step, new nodes and new edges are added to the network. So you can see that while in the ER model, the size of the network is fixed in advance, in growing network models, the size of the network changes with time. This is a key feature that in many real-world networks has. So now we move on to explain referential attachment, which is perhaps one of the most important growth mechanisms in network science. Let us denote the probability that node Vi gets a new edge at time step t as PIT. In the PA mechanism, this probability is proportional to a KIT, in which KIT is the degree of node Vi at time step t, and AK is the referential attachment function at k. So referential attachment is a richer mechanism. The more edges a node currently possesses, the more edges it will get in the future. So we can actually prove that in growing network models with referential attachment, the degree distribution will have heavy tail. In this figure, I fit a growing network model with referential attachment to the Google Plus data and then plotted the degree distribution of the fitted model. We can see that the PA model can capture very well the observed degree distribution. So growth and referential attachment are two key features that can reproduce the heavy tail degree distribution in real-world networks. So the question is, how do we estimate the PA function from the observed data? So the problem formulation is simple. We are given a time series of growing networks observed at multiple time steps. GT is the network snapshot observed at time step t. Our goal is to estimate the value of the PA function from A0 to A capital K, in which capital K is the second largest degree observed in the data. So for this problem, there is a standard method which is called Newman's method. It is a popular method which was applied to many real-world networks to estimate the PA function. However, in all the results, there was always this strange behavior of the estimated values. In the figures, the horizontal axis is the degree and the vertical axis is the estimated PA value. So we can see that the estimated PA value always fall up when the decrease is large. So for more than 10 years, no one knew why. So our first work in this topic is to point out that this strange behavior of the Newman's methods is actually a bias. We figure out the cause of the bias is that Newman methods wrongly assume that all the decrees appear from the start. We found out that if we use the correct appearance times of the decrees, then we can construct a new method that does not suffer from the bias and can estimate the PA function reasonably well. So in addition to the PA mechanism, we also propose estimation methods for other mechanisms. For example, in this publication of ours, we propose a method for the joint estimation of referential attachment and node fitnesses. In this figure on the left, this is the estimated PA function, and in this figure on the right, this is the estimated fitness. And in another publication of ours, we propose a method to estimate jointly referential attachment and transitivity. So you can see here is the estimated referential attachment function, and here is the estimated transitivity function in 3 real-world networks. So we also provide a package that implements our proposed methods. You can search for it on Cran. So now I have finished my review of the problem of estimating growth mechanism with time series data. We will now move on to a much more interesting problem of estimating referential attachment from just one single snapshot. So the conventional setting is that we observe a time series of multiple snapshots observed at different time steps. However, what if we can only observe only one snapshot at time step capital T? Can we estimate the referential attachment function from only G capital T? So why do we want to consider this obviously harder setting? The reason is that the number of real-world datasets that contain only one snapshot are actually larger than the number of datasets that do contain time information. So if we can find a method for estimating the PA function from just one snapshot, then we can start to analyze a much larger number of networks. So our approach in this problem is to exploit the information about the referential attachment function in the limiting degree distribution. Let us denote the number of degree k nodes at time step small t as nk small t with some assumptions on the growth process of the network. We can show that when t tends to infinity, equation 1 holds. So from equation 1, one can construct a simple baseline method. First, when capital T, when the time step capital T is large enough, one can obtain equation 2 from equation 1. And in order to use equation 2, we need to estimate the true expectation in the denominator and in the numerator. So we are going to estimate them by the observed value in the snapshot G capital T. And after doing so, we arrive at equation 3. This is the estimation equation of the baseline methods. So this equation can be calculated from just one snapshot at time step capital T. So however, when we apply this baseline methods to some simulated data, we noticed that although the estimated value of AK when k is small is very good, the estimated values of AK started to fall up when k is large. So we call this a waterfall artifact. So what is the cause of this artifact? So to understand this artifact, Let us review what we actually need. What we actually need is the true expectation in equation 2. However, in order to apply equation 3, we notice that we only choose the degree where nk capital T is positive. Therefore, nk capital T is not an estimator of the expectation of nk capital T, but of this conditional expectation, which is conditioned on the event that the degree k exists in the snapshots. So this is a selective bias in which we forgot to consider the probability that the degree k exists in the observed snapshot. So let us denote the existence probability of k as pk. Now we can see that the baseline method is equivalent to estimating pk equal to 1 for on k. However, as we can see on this figure on the right, the true values of pk fall off dramatically when k is large, and therefore setting pk to 1 for on case is actually pretty bad. So this is what causes the waterfall artifact. Now, since we understand the cause of the artifact, it is easy to propose a method to remove it. Denote the estimator of pk's as pk hat. Using pk hat, we arrive at equation 4, which is the estimation equation of our proposed methods. We then use Monte Carlo simulation to iteratively calculate pk hat. As you can see on the figure on the right, the Monte Carlo simulation works well in estimating the existence probability, and this completely removes the waterfall artifact, as can be seen from the figure on the left. So to conclude this session, I will show some example when we apply the proposed methods to some real-world networks. We compare our methods with the gold standard, which is the maximum likelihood estimation with full-time information. So this is the maximum likelihood estimation with full-time information depicted in red. So we can see that the proposed method is much better than the baseline and is comparable to the maximum likelihood estimator, although its variance is a little bit bigger. So finally, I will talk about our work on the role of referential attachment in condensation in fitness models. So in this session, we consider a popular extension of the referential attachment model, which is the referential attachment with multiplicative fitness. Recall that PIT is the probability that node VI has a new edge at time steps t. So in this model, this probability is proportional to the product of the referential attachment value and the fitness Fi of node Vi. So this model captures heterogeneity between nodes with the same degree. So in fitness models, there is a fascinating phenomenon called condensation. Based on the model parameters, there exist nodes with a very large number of edges. The true figures show true simulated networks with the same initial state and the same parameter setting, except for the PA function. On the figure on the left, the PA function is k plus 10. And in this network, condensation did not occur. And in the figure on the right, the PA function is k plus 1. And in this network, there is condensation. We can see that there is one node with a very large degree. So what is condensation exactly? So the name condensation has origin in physics. So there is a mapping between a growing fitness network and quantum particles that give the physical explanation to condensation. In this mapping, an edge is regarded as a particle, and each fitness value defines an energy level. So in this figure on the right, there is an energy diagram, and each dot in this diagram represents an edge in the network, and each line represents an energy level. So in condensation, most particles concentrate at the lowest energy level. So this is equivalent to the case that in the network, most edges connect to the node with the highest fitness. So although the condensation phenomenon has been investigated by the complex network community for a long time, all existing was either assume the function from ak equal to k or ak equal to k plus 1. So however, we know that the estimated PA function in a large number of real-world networks are not of this form. So our goal is to investigate the condensation phenomenon with a tunable PA function of the form k plus c, which c is a positive parameter. When c is large, the PA effect is weak. In this case, the nodes are chosen nearly the same as uniform sampling. So when c is small, the PA effect is strong, since the initial differences in the degrees between nodes are emphasized. So we want to understand how condensation changes when the strength of the PA effect varies. So in order to investigate condensation, we need to make some assumption. First, we assume that the number of nodes at time step t scale like p times t, and we assume that the number of edges at time step t scale like 1 minus p times t. Here, p is a parameter that controls the ratio of nodes and edges in the network. Secondly, we assume that the fitness distribution is continuous on 0, 1, with the essential supremum being 1. And we denote mu as the fitness measure. Now we determine the constant lambda star as follows. If this condition is satisfied, we define lambda star as the unit solution of this equation. So when this condition is satisfied, this equation is guaranteed to has one unique solution, and we define that unique solution as lambda star. And if this condition is not satisfied, we define lambda star as 1. So now we consider the measure gamma t defined by this equation. So this is the empirical measure of fitness of a node belong to an edges that is sampled uniformly at random at time step t. So for example, gamma t a b is the proportion of edges whose nodes possess fitness in the open interval in the interval a from a to b. So we can also see that the value of gamma t at 1 is 0. Since there is no nodes with fitness 1, so since we assume that the essential supremum is 1, so there is no nodes with fitness 1. And then we have the following result, which is a key in understanding condensation. When t tends to infinity, the measure gamma t converges to the following measure gamma defined in this equation. So let us look at this equation. So the condition for condensation is this condition. So we can see that if this condition is satisfied, then this quantity is positive. You can see that this, if the condition is satisfied, then this quantity is positive. And when this happens, the term delta 1 in the limiting measure t remains. So we can see that the value of gamma at 1 is positive even when the value of gamma t at 1 is 0 for any finite t. So this is the mathematical framework behind condensation. It is a mass escape to infinity situation. So since some nodes will get so many edges, when we consider the degree weighted fitness distribution, an atom appears at the essential supremum in the limit. So let us look at the condition for condensation. This is the condition for condensation. So from this condition, we can understand when condensation happens. Firstly, condensation happens when the ratio P over 1 minus P is small. This happens when the average degree is high. So we know that P over 1 minus P is the ratio of the number of edges and nodes in the network. So P over 1 minus P is small, this implies that the average degree is high. Secondly, condensation occurs when the expectation of F over 1 minus F is small. This can happen when the fitness distribution concentrates near 0. Finally, condensation can happen when C is small. We know that when C is small, the referential attachment is strong, since the initial differences in the degrees are emphasized. So it implies that a strong referential attachment effect facilitates condensation. So while the first and second situation have been proposed previously, this relation between the strength of the PA effect and condensation seems to be new. So to summarize my talk, in the second part, I talk about how to estimate the referential attachment function from one snapshot. In this situation, since there is a hidden selective bias, we have to correct for the probability that we observe the degree k in the snapshot. So the moral of the story is that one has to look out for hidden selective bias when the data are not IID. And in the final session of my talk, I talked about condensation in fitness models. I showed that a strong BA effect encourages condensation, while a weak BA effect impedes it. So there are some very interesting open problems in this direction. Firstly, problem of detecting condensation in network data is a hard problem that is still not solved yet. But secondly, it would be very interesting to see what we can say about condensation under other forms of the PA function. So this talk is beyond John was with the following people. So this concludes my talk. Thank you for your listening.
One question. So how do you measure the hidden selective biases? How do you measure the hidden selective biases? This is a question.
Yeah. I assume that you asked about selective biases in the problem of estimating the referential attachment from one snapshot. So the key is to estimate the existence probability. The key is the estimating this existence probability, and so we start from some. We start from the initial value of the baseline methods, and then we use simulation to iteratively improve the estimation. So that's how we correct for the hidden selective bias.
So we run simulation, yes, and then observe how many times we observe these k values. Yes, and then use the updated parameter to run next simulation, and then repeat that how many times?
About 5 times.
5 times.
Yeah, 5 to 10 times. Yeah.
Okay, so next question. For small sample size, are there any additional tests to measure impact on bias? For small sample size, are there any additional tests to measure impact on bias? Small sample size means if the network, the number of nodes, or it's small network probably. What do you mean? What do you think, Fang?
Let's see. I do not understand the question very much, but it's just
so could you clarify the question? So what do you mean by small sample size? Number of nodes, maybe. Yeah. If the network is very small, then yes, everything could be very difficult.
Yeah, it's very difficult. Yeah. So you can see that's a basic assumption of our method is this the capital T is large enough. It means that we can exploit the limiting degree distribution. So when the number of nodes is very small, then this limiting degree distribution does not hold, and maybe it's basically impossible to remove the selective bias in this case. Yeah.
So if the number of nodes, number of nodes is very small, like a 10, then the method won't work, right?
Oh yeah, but maybe in this those cases we have to use some computational methods, just a MCMC. Yeah. Yeah.
Okay, nice question. Thank you. Yeah, for the question. Yes, no question more. All right. Thank you, Pham, and thank you all the speakers. And also thank you for the listeners, audiences, for for listening to for a long time. And thank you very much for everyone. I would like to close the seminar. Okay. Thank you very much.